questions on practice question set number 30, which of course is on concepts 49, 50, and 51, which was half-life, fission, fusion, I believe. And I believe this was on Rutherford. If I remember, though, there is a concept 52 on there, a Bohr model the atom question on there as well, I believe. So let's take a look at question number one, which numeric response number one, arguably maybe the hardest half-life graph question that we've seen in the last 20 years. It's not insanely hard, but it's definitely harder than average. Usually it's just read straight over and straight down, and that's what we got, or up and over, that is. And that's what we got to do here too, but there is a little bit more to this one than just that. We've got percent remaining on the left-hand axis, so the y-axis, which of course is n, and on the x-axis we've got time, which they've given it to us in hours here. It could be in seconds or days or years or whatever. And then it asks us, how much time does it take for 40 grams to decay to 1.25 grams? And as soon as I saw this, I don't know about you, but I go up here and I'm going to go to 40 grams and go over and down. But then I realized, wait a second, the y-axis isn't in grams. It's in percent. I'm like, well, that's not so bad. Let me just figure out what 1.25 grams is as a percent. It works out to be 3 point something percent. So then we go over like 3-ish percent over and down. Oh, where exactly is it? Like, where does it intersect? Because this is numeric response. We want to be bang on, right? If it was multiple choice, if we're close, we're gonna see which one is the right answer, right? But if it's numeric response, we want to be bang on. Anybody have another option here? It's a graph, so you know you're going to do up and over or over and down, but you might have to do something else too. Caitlin? Find n, the number of half-lives. Okay, we can do that. I'm going to use my little chart for that, although you could use logs, right? 0 half-lives. Somebody this morning, we were doing a question, and they started with 1. 1, 2, 3, 4, 5. Don't start with 1. Start with 0, right? Because after 0 half-lives, you've got what you started with. If you say after 1 half-life, you've got what you started with, then you're going to end up with an extra half-life in there. N is going to be 1 higher than it should be. So 0 is 40, 1 is 20, 2 is 10, 3 is 5, 4 is 2.5, and 5 is 1.25. So yeah, Caitlin, the number of half-lives is 5 here. Hey, how's that going to help me though? How's that going to help me in this question? Kobe? Sure, find the half-life on the graph. And that's a much more precise reading on the graph. We start with 100%, we go down to 50%, and it's exactly 0.6. 0.6 hours. So now if we say n is equal to t over t1 half, t is equal to n times t1 half, it's 0.6 hours times 5, which gives me 3.0 hours. So my answer is 3.0 hours there. Good. And then look, when I look back to my original here, it looks to be pretty darn close there, right? Just hard to get that exact number if we just went over and down the first. Good. How many people got that 3.0 hours? It is 2 digits, by the way, right? Okay. Usually we expect to get 3 digits in there. So if we're expressing just 2 digits, 3.0, remember that you always start on the left-hand side and you leave the last box blank. So it would be 3.0 and you just leave that one blank. It doesn't happen often, but it does happen that we have to leave something blank. Okay, next question is a half-life calculation. This one is more straightforward. This one is like pretty typical actually of what we might see. 6 hours is the half-life. 24 hours have gone by. That means n is going to be equal to 24 divided by 6, which is 4. And we want to find how much remains. So let's just say n is equal to, we start with 100% times 1/2 to the little n, which is 4. And I think that works out to be B, 6.25% when we do the math there. Is that right? Okay, so B is our answer then. 2 isn't really a unit, this unit question. This is really an EMR question, right? We're given the energy of a photon. We want to find the wavelength, but it went with this scenario above, so I just tossed it in there anyways. If you want to find the wavelength, given the energy, we're going to say E is equal to 8C over lambda and rearrange it. Lambda is equal to 8C over E. Now, You got to be in either joules or electron volts. We're in mega electron volts here. So I'm going to convert that to electron volts. 3.85 mega electron volts is the same as 3.85 times 10 to the 6 electron volts. You can use that for your energy. If you do, just make sure you use 4.14 times 10 to the negative 15 EV times seconds. If you're not comfortable with that, you just can't figure out when to use joules and when to use electron volts, what should you do? Always use joules, convert this to joules, use the 6.63 value. Any way you look at it, you're going to end up with B as an answer, 3.23 times 10 to the negative 13 meters. This morning when I was doing this, I didn't have an answer key in front of me, but I knew the answer wasn't going to be C or D. I don't remember off the top of my head which wavelength is gamma rays. I do know visible light is 10 to the minus 7. Gamma rays, I don't remember. But I knew it wasn't going to be C or D, because if visible light is 10 to the minus 7, gamma rays have a higher frequency, therefore they have to have a lower wavelength. And 10 to the 12 and 10 to the 20 are definitely not lower wavelengths than 10 to the minus 7. 3. Here's another half-life thing, but this is one of those logarithm / divide by 2 method questions. 0 half-lives, I've got 1.45 kilograms or 1,450 grams. 1 half-life, 725. 2 half-lives, 362.5. 3 half-lives, 181.25. Is that right? And then 4 half-lives is 90.6 grams. So we do have 4 half-lives. We want to find the half-life. So it's going to be what? 32.2 divided by 4, which is 8.05 days. So the test that I just finalized last night, I can tell you that there's at least 1 half-life calculation in there. I want to say, I can't remember for sure, but I want to say it involves one of these divide by 2 things or logarithms. Okay, be ready for that. Be ready for that, just in case. Okay, I'm not positive, but I think it's one of those questions. Definitely a half-life thing, though. Okay, next question. Here's a good one. This is one of our Venn diagrams. We've seen, I think, one more Venn diagram question earlier on this year. You guys know what a Venn diagram is, right? So those diagrams used in math class all the time, right? Pair of things. Fission and fusion. If it's fission, just fission, it's 1. If it's just fusion, it's 2. If it's both of them, it's 3. And if it's neither one of them, it's 4. Right, Nico? So what do we got here? The measurable mass of the product is less than the measurable mass of the reactants in a spontaneous reaction. What is that? Fission or fusion or both or neither? 1, 2, 3, or 4? It's going to be 3. That's going to be both, right? We have a mass defect in both cases, and that's why we end up having energy released in both cases. Now, the second one, this one's a bit trickier. The kinetic energy of the system increases in a spontaneous reaction. I said 3. Okay, I said 3. I said fission and fusion. But I'm going to explain one more possibility after we're finished going over the rest of them here. How many of you guys said 3, by the way? Okay. And that's absolutely correct. Okay, it's absolutely an acceptable answer there, but there is one more option that we'll deal with in a second here. This reaction, what kind of reaction is that? It's fission. It's reaction number 4. Sorry, what was fission? 1. It's reaction number 1, which is fission. It does look a little bit different. Usually we see it 1, 0 neutron plus this, 235. But then remember that becomes temporarily, for a short period of time, uranium-236, which decays. So it is fission. It just looks a little bit different. Bottom line is 1 big becomes 2 smaller nuclei, so it's still going to be fission. And the last one, this is just alpha decay, so this is going to be number 4, neither one of fission or fusion. Now, let's go back to this one for a second. Sometimes I go back to an answer key that Alberta Education gives us. Sometimes they don't even give us an answer key. This one they did, and I remembered where this question came from. So I went back and checked the answer key just to double check that one. And they marked 3314 absolutely correct, but they also marked 3114 as correct as well. And here was their explanation. And I wouldn't have got that. I wouldn't have got the 3114, but that's okay because 3314 was also marked correct. The reason they marked 3114 is correct is because in certain situations in advanced physics, the kinetic energy of the products of a fusion reaction is not greater than the kinetic energy of the product, than the kinetic energy of the reactants. So that would mean that it would have to be just fission as opposed to fission and fusion. Okay? Now, they didn't mark 3114 correct because they expected you to know that. Okay? I wouldn't have got that. They marked 3114 just in case you knew that. Does that make sense? You didn't need to know that. Okay? I wouldn't have got that right myself. I wouldn't have got that aspect of it right myself. But I would have got the question right because in most situations, the kinetic energy is greater in both fission and fusion. But if you somehow just happen to know that it wasn't always the case, then they're not going to penalize you because you knew more than you were expected to know as well. Does that make sense? Did anybody actually put one for that? No? Okay. So 3314 is the answer that I would definitely go with. And hopefully is the answer you had. 4, Rutherford planetary model of the atom had to be revised because of Maxwell's theory of EMR, accelerating charges release EMR. Of course, we know that electrons in the Bohr model of the atom orbit around in a circle, and that's a centripetal acceleration toward the center of the circle, but they don't emit EMR. So we say it's in a stationary state. It's as if they're not moving. Rutherford's atomic model, teacher lined up 5 students and threw beanbags at them. Sounds like fun. Beanbags are way heavier and way more hurtful than pieces of paper that we're throwing at somebody, right? Like we did in class here. This would be something similar to the Rutherford experiment, right? Most of the beanbags would hit empty space, but then the odd beanbag would hit somebody and deflect off of them, and then the odd beanbag would bounce off of somebody and come straight back. So this would be Rutherford's experiment. The beanbags would represent the alpha particles, and the people that they bounce off of or miss would represent the nuclei. And 6, when white light passes through a cool gas and then through a spectroscope, the spectrum produced is what? We will review this stuff in a few moments because we just did this on Friday, right? One time so far. But I'll remind you, when white light passes through a cool gas, the cool gas, cool, is going to absorb. So when we absorb EMR, we're going to get an absorption spectrum. A continuous spectrum is produced by a hot solid or a hot liquid or a hot gas under high pressure. And a bright line spectrum and an emission spectrum, the emission spectrum is just kind of a catch-all term for continuous and bright lines, so it wouldn't be that one. A bright line spectrum is produced when you have a hot gas under low pressure. And again, we'll spend a little bit more time on that with the diagram in a moment here. The answer is B. And finally, the last one, I like this question. A fluorescent light tube contains a gas mixture at a low pressure. When a current is passed through the tube, okay, we're putting energy into this if we're putting a current in, right? So what happens when you put energy into this? Electrons are going to jump to a higher level. And then what happens? Well, they want to go back down and fill in the vacancies, right? So what's going on here? When a current is passed through the tube, electrons jump to a higher level. That doesn't produce EMR, but when they fall back down, that produces EMR. The answer for us is going to be B here, because the electrons of the gas atoms are initially excited to higher levels, and then, it doesn't say this, but then they're going to go back down to lower levels, giving off EMR. According to Maxwell's laws, we never talked about Maxwell in this context, transformed to vibrational energy in the atomic band. That doesn't sound right. An electric current is scattered by the nuclei. Boy, this is like, we can't think, this is like, we can't think of an answer, a good answer, a good fourth possibility. So we're just going to make something up, completely make something up. Let's try to make it like something like you've heard before so that maybe we can trick you. Kind of like the Rutherford experiment, alpha particles are scattered, but no, you're not going to scatter an electric current by the nuclei of these gas atoms. That has nothing to do with the Bohr model. So the answer is B. Good.